Hey, in this video, I'm going to explain about the weak heaps and its sorting algorithm. Lecture by Charles Hughes from the course Design and Analysis of Algorithms. Here, first, in order to understand the weak heap, we need to know what a heap is. Heap is a complete binary tree in which all the nodes have left and right child, leaving the leaf nodes. Heap can be a max heap or a min heap, wherein root having largest value among all nodes is a max heap, and root having the smallest value among all nodes is a min heap. So, a weak heap is definitely defined by relaxing the requirements of a heap. So, let's see the requirements here. The value in any node is at least the value of any node in its right subtree. The root has no left subtree. Nodes having fewer than two children except the root appear on the bottom two levels of the tree. So, from the below example, it's clear that given node is always greater than the node in its right subtree. Here, the root has no left subtree, and other than the root, the bottom two levels of the tree may or may not have two children. Thus, this tree satisfies the three requirements, hence it's a weak heap. So, how to merge two weak heaps? Two weak heaps can be merged by following the given rules. The root node containing the largest value among the trees will be taken as the root node of the merged tree. Next, the second requirement is the smaller root becomes the right son of the merged tree, and the remaining tree of the largest root will be the left subtree of the smallest root. Below example depicts this. Here, the tree is given in green has the largest root value. Here, let's see in step by step how the merging happens. In step 1, we separate the largest root value from the tree. Here, it's green tree with value 15. And in the step 2, according to the given rule, we add the smallest root value subtree to the right of the largest value subtree. Now, we use 15 as the root to the merged tree, and the rest of the green tree goes to the left of the orange subtree. So, this newly formed tree satisfies the properties of weak heap, which are mentioned in the left. The value in any node is at least value of any node in its right subtree. So, it is satisfied here between 12 and 15, and also 10 and 9. The root has no left subtree. Yes, the root 15 has no left subtree. Nodes having fewer than two children except the root appears on the bottom two of the levels of the tree. So yes, it is satisfied. Now here for a given node h of I, here h indicates the array or the number of nodes, the total nodes in the given weak heap. Left child is h of 2i, I is the index, so 2 into I is 0. So at the 0th index level, it doesn't have any left subtree. And coming to the next thing, right child is h of 2i plus 1. So if we take for the 0th index, h of 2 into 0 plus 1, it's 1. H of 1 has both left subtree and also the right subtree. So how to represent weak heaps in memory? One way to do it is to put them in an array. This can be done in two ways. Array for a binary heap, which is it is same as the breadth first search, wherein we place the values in the array based on the index. The next type is reverse array, Boolean array, where we can indicate which node is in the left and right child of a given node. If the value in the array for an index is 0 or true, then the value has right child. If it's 1 or false, then value has left child. Now let's see example of for a binary tree or a binary heap. For the given weak heap, all nodes are given the indexes and n indicates the number of nodes, which here is 8. So in order to represent it in an array, they are placed in array according to the index values 0 to 8. and length of the array should be n plus 1. Here it is 9. So here for a given node h of I, left child is h of 2i and right child is h of 2i plus 1. Here h is the array and I is the index. And the values in the root in the given heap are placed in the array according to the index values. Coming to the reverse array, it is represented in the form of Boolean values 0 and 1. Here H binary tree array of the given tree and R is the Boolean array of the given tree. Now if the value in R array for an index is 0 or true, then the value has right child. If it is 1 or false, then the value has left child. True or 0 when it is the node 2i and false or 1 when it is node 2i plus 1. Suppose for 15, index I is 0, then 2i equals 0, then it has right subtree. Next, if I is equals to 1, then 2 into 1 is 2, which is 14. It has left subtree, so the value becomes 1. Next, if I is equals to 2, then 2i plus 1, which is 5. In turn, the value at index 5 is 13. This means 13 is the right node of 14 and is given 0. So same follows with the rest. So now we know the merging and reverse bits and also the array representation. Let's see how sorting works for weak heaps. So here the algorithm calls weak heap sort, which in turn calls the weak heapify function. Here the given weak heap is a forest of weak heaps. So the root node will be the largest value and is taken and placed in the last cell of the array. In the next iteration, it walks down until the last cell, leaf node, and carries the split operation following the same for n-1, n-2 levels until the root node. Now, using the merging, the splitted trees and merged one after the other. The newly formed tree's root value is taken and placed in n-1 position of the array, and the process goes on until the nodes are traversed. Now let's see sorting with an example. Given the weak heap, the binary heap values are placed in arrays as per the index values. So here shown the same. Next, sorting by splitting and merging. Here, as it is weak heap, the value at the root node holds the highest value, so it is placed in the nth position of the array. Now, the tree is traversed to the leftmost subtree and splits the left nodes as shown here. So, the highest root value 15 is placed in the last position of the array. Now, using the merging property, the trees are merged based on root value, and the subtree of the largest value is placed left to the smallest root value subtree, and in turn it will be the right subtree of the root of newly formed merged tree. Now the root is the highest value and is placed in n-1 position. Here 14 is the largest root value after the merged tree. So it is placed before 15, which is n-1 position. So this continues until the splitting and merging of the cells until the root value is found, and then it is placed in the array in n-1 I position. The same follows here. The tree is being splitted to the leftmost subtree, and then it is being merged, and the root value is being placed in the array. This continues until the complete tree is splitted and one node is left. So here the 8 is left. So the sorted array is formed, then which is more efficient. Here shown the sorted array of the given heap. Now, so following can be the improvements of weak heap algorithm. The entire sorting can be done using the extra memory position, reducing the memory usage. As the reverse bits are available, all the branch swaps can be obtained in an array. Weak heap is a fast in time algorithm and is considered the fastest among others till date. Thank you.